Have you guys ever wondered how computers have ultimately made our life a lot easier compared to many years ago? All of that comes down to a lot of quantum computing, and Mr. Keith Motes is a PhD student from Macquarie University. He originated from the United States of America in
Louisiana.
Yep. And he's here today to bring you guys a presentation to kind of give you a brief idea of what it's like to be in quantum physics and how it applies to our world today. So, Mr. Keith Motes.
Thank you. Okay, so how's everyone today? Doing alright? Excited? Okay, so I'm going to tell you a little bit about my journey in quantum physics. I'm going to talk about what led me on this path, a little bit about what I do as a PhD student. And of course I want to also tell you a little bit about what quantum is, hopefully boggle your minds a little bit with some of the interesting properties involved, and even talk about how it may change technology this century. So let's get going. So in my talk, I'll mention my personal journey, then talk about the properties and how it will revolutionize this century. So my journey, I would say it began for me when I was a kid watching Discovery Channel and Science Channel and stuff. Those are always my favorite shows to watch, like especially about dinosaurs and things. And also I was fascinated with playing billiards, which you can imagine has a ton of physics involved. You have to deal with angles and spin and momentum, all these physics concepts that as a kid I just visualized. I didn't know the physics behind it, obviously, but I was able to, over time, visualize and get pretty good at pool. Okay, and then in high school, my favorite course was obviously physics. There was a teacher, the physics teacher, he was this guy with a very unique body odor, and he taught there for like 20 years, and his room totally smelled like his unique body odor, which was not pleasant, and it scared most people away from even doing physics in high school. But nonetheless, I did it, and I loved it. I got awesome grades, just not even trying very hard. Later, I went to a community college where I majored in science and chose to be a physics major, but they didn't have a physics program here. It wasn't until later when I graduated from here and went this was a physics professor. The only physics class they had at that community college was by a guy, Dr. Roy, and he kind of looked like this guy in the cartoon. It's pretty cool. And then while I worked at this place, I began privately tutoring in like mathematics and physics, which was pretty awesome because I got to share what I learned and even learn it better than just taking the course. And also waited tables, but then one day I was like, you know what, I'm tired of doing both of these things, I want to focus on physics. So one day I just up and quit both jobs at the same time in one day and began privately tutoring on my own. So just charging my own rates, meeting with students who were interested, and this fared a lot better for me because I only worked a few hours a week and had all the time, all the money I needed to live, and all the time I needed to focus on my studies. So hopefully this may inspire you to do something similar. Okay, and then I moved to Louisiana State University. There's an image of the clock tower. They have the ninth biggest stadium in the world, and they even have a live tiger on the campus, which is pretty cool. Here I began teaching as a supplemental instructor, is what they call it over there. So that was an awesome experience. I taught a physics class. It was electricity and magnetism, and it was because it was kind of, I chose to do this. It was kind of ego-based because it was the first class I ever got a B in university. So it's like, dang it, I gotta learn. I gotta like get better at this subject. So I was like, I started teaching it, and yeah, it was cool. So, and then I got into quantum research with this guy, Jonathan Dowling, crazy quantum physicist, but very awesome guy. He's helped me out a lot. One thing that I started learning right from the get-go was Mathematica. It's a programming language it's just awesome. Later, I did my first internship in kind of engineering physics at the Massachusetts Institute of Technology in Boston. And yeah, it's really my first working experience in physics, which was nice. And then I move on to later a second internship at the Institute of Quantum Computing in Canada, where I really got to do work in quantum. Like, it was really my, I would say, other than doing quantum research back at LSU, it was my first time to kind of travel the world to do quantum, and it was an amazing experience. And by the way, that's one thing you get to do a lot as a PhD student, is travel. I'll get to that more in a little bit. And then, okay, I come back from this place, Canada, and I wasn't sure what I was going to do. I just finished university. I got my bachelor's, and I had no idea where I was going to go to grad school yet, but I knew that's what I wanted to do. And I was driving with my girlfriend at the time around New Orleans, Louisiana. We were passing the Superdome, which is this huge stadium that looks pretty awesome. And I'm driving, and a shooting star shoots across the sky. All of a sudden, I'm like, whoa. And then a few seconds later, I get a vibration on my cell phone. I look at it, and it's my PhD advisor, and my current PhD advisor at Macquarie University. He is texting me congratulations on getting accepted. So I was like, whoa, this is awesome. I felt so good, and I looked at my girlfriend, and she was pretending to be excited, but I could tell she wasn't really, because she knew that meant I was going away. Anyway, so I go to Macquarie University. Nice campus. I don't know if you've ever been. Has anyone been to Macquarie? No? Yeah? Yeah, so you get a nice little campus there. These are my advisors, Alexei Gilchrist, Peter Rody, and they're awesome advisors. They help me quite a lot. They're always there for me, and they've helped me have a very productive PhD so far. So speaking of, let me tell you a little bit about what it's like to be a PhD student. So, at least in physics, this is my experience. What you get to do is, one thing, you get very good at programming. So, in various languages. So imagine, as a physicist, I imagine some physical system. In my case, quantum particles or quantum light or whatever, and I devise some system, and then I have to simulate it with a computer, because I can't do it all by hand. It'd be impossible. It'd take too long. It'd take my whole PhD just to write out the calculations. So I have to program it in a computer, and after a while you get quite good at programming, which is very useful in life. Does anyone here know any programming languages? Yeah, one, two, a few of you? Yeah. So I don't know about you guys, but I really enjoy it. I get the chance to public speak a lot, like right now, which is a valuable skill, and for me it's fun to share my experiences. I get to travel to different conferences and collaborate with different people. So I've been to Tokyo to collaborate with someone, and there I got to give a talk. I've been to conferences, like I've been flown all the way to America just to give talks, not like this, more scientific, but about my research, which is something pretty cool to do. I've been all around Australia since it's a lot cheaper to fly me to like Brisbane or Melbourne or Perth or something. I get sent to these places quite often every year to work with other researchers, to give talks kind of like this, and just do research, which is pretty cool. And by the way, in Australia, as a PhD student, you just do research, you don't have to take classes, which is one reason I came all the way here from America to do my PhD, is I didn't have to deal with classes, I could just jump right into the research, which is really what I enjoy. So, writing, of course, you do some research and you have to write about it, you have to let the world know what it is that you did, what you found out, etc. So you get the opportunity to write very scientific papers. And even in arts, if you do a PhD in some sort of art or something, you still write as well. And it's some aspects of science in it, but in my case, it's very scientific. So you get to deal with publishing papers as well. So you write it up, and it's a whole process dealing with publishers who have to give you feedback, and they have to send it out to referees to make sure your work is accurate, and then you have to make editorial changes. So it's a cool process to learn. Traveling, I spoke a little bit about that already. I've been all over. I've been to a conference. I got flown to give a talk at a conference at a ski resort, and there I am. I was actually snowboarded the whole time. It was awesome. I did give the talk there. Yeah. Recently, I got a chance to even do filming, so I'm doing this short segment of. It's called Quantum Breaks. Each one is about a 5-minute video where I get to go interview someone, and they tell me about their research, and hopefully these will be going on YouTube pretty soon. You learn language. Like, what I mean by that is programming languages, like mathematics, physics. It's all a language, and you get good at using it, and it's quite enjoyable. And also, you have time for fun. Like me, a lot of people get stressed out, like feeling like they'll have to work all the time. But I make sure I take time for myself. Like recently, I took a few weeks in Byron Bay, a few weeks in America. I take camping trips all the time. Like, I have time for fun. I recently did yoga teacher training where I took off heaps of work to do all this. So, yeah, so as a PhD student, your life isn't like a prison. You have time to do other stuff. So, let's get into the next part, which is some mind-boggling quantum properties. So, in the quantum world, this is an acceptable answer. So, hey Schrodinger, what's in the box? My cat. Oh, is it alive or dead? Yes. And you'll see why in a minute. So, first of all, what is quantum physics in a nutshell? It's the study of how the world works on the very small scale. So we're talking atoms or photons, which are individual particles of light, and among other things. And because they're so small, they behave quite differently than we're used to in the classical world, like my laptop or your shirt or your book sack or a camera or whatever. And I'll get into a little bit now how they behave differently. And these are some cool images of just a hydrogen atom at different energy levels. And you can see that depending on their configuration, they look quite, it looks quite unique. And these are actually, realistically, they're 3D models, but these are 2D slices. Okay, so, one of the first quantum properties that we realize is that things are quantized. This means that there are only discrete units of energy something can have. It's not, what I mean by that is you can have 1 unit of energy or 2 units of energy or 0, but you can't have like 1.5, for instance. Whereas in our classical world, we can say you have 1.6789, whatever unit of energy you want. So, this realization actually led to the laser in the last century, which, as you well know, has revolutionized technology. Like so many things, like telephone calls through fiber optic cables, laser printing, laser surgery, cutters with lasers, all sorts of things. Okay, so another one is quantum tunneling. So the idea is that, imagine you have a hill and you want to go over it. If in our classical world, you have to actually pick up the rock or ball or whatever it is and bring it over the hill. You have to give it enough energy to make it over the hill. But in the quantum world, with some probability, the particle will tunnel through the hill without giving it the energy that you would require classically. So this is a bit bizarre, getting a little bit weirder. This sort of realization led to things like the transistor, which is used in all computer chips ever. And obviously, I think we all know how computers have revolutionized our world. I'm using one right now to give you this presentation. Another one is wave-particle duality. So this is the idea that light, or even matter in general, is a wave and a particle at the same time. So let me expand on that a little bit. So imagine you have a particle like an atom, and in quantum mechanics we say this atom is represented by some probability wave in space and time, and this probability wave represents where it will be at a certain position at a given time, and this is pretty cool, because if you measure it, you see a particle at some spot, but before you measure it, it's thought to be in all of these places simultaneously as a somewhat probability wave. So next, the uncertainty principle. So I'm here for you, the girl says, and then the guy says, great, now I don't know your velocity. So this comes down to Heisenberg's uncertainty principle. Of course, it doesn't really work like that in the classical realm, but in the quantum realm, the more you know about something's position, the less you know about something's velocity, or its speed, and vice versa. So it's like the more you learn about something, the less you know about something else. And this is pretty bizarre. This doesn't happen in our classical world. If we know, we can, with a car or an airplane, we can know exactly where it is and how fast it's going at the same time. This is impossible in the quantum world. So, getting to more bizarre properties of quantum mechanics, which will be harnessed more this century to revolutionize technology even more. So far, the properties I presented have made things like lasers and transistors. They're some of the more basic properties of quantum mechanics. But now we're getting into some of the ones that we're really starting to tap into now and in the coming decades. And one of them is quantum entanglement. So it's the idea that particles, you can entangle them such that they are correlated with each other, and you can move them to opposite sides of the universe as far apart as you want. But when you do something to one, you know exactly what happens to the other one, no matter how far apart they are. So this is entanglement, and we can actually use this property of quantum particles for things like measuring stuff more precisely. Like we can use it for imaging individual atoms, which is pretty cool, among other things, quantum computing, etc. So another thing, by the way, if you have questions, feel free to raise your hand and ask at any time. So quantum superpositions. So this is the idea that things can be in more than one place at the same time, or they can be in more than one state at the same time. And there's Schrodinger's famous cat example of the cat being dead and alive at the same time. So the way it works is you put a cat in a box with a radioactive atom, and since the atom is a quantum particle, it obeys the laws of quantum mechanics. So if it's set up such that if the particle decays, it flips a switch, which breaks the flask of poison, which kills the cat. And if the atom does not decay, it does not flip the switch and it does not kill the cat. So when you close this box up, you know quantum mechanically there's some probability of the atom decaying. So before you open the box, the cat is in a superposition of dead and alive because it's entangled with the atom, which is in a superposition of decayed and not decayed. Did everyone get that? Okay. And there's teleportation. Not to be confused with like Star Trek type teleportation. We don't know how to do that. But there is teleportation in quantum information where we can teleport quantum information, but it requires a classical channel to transport some other bits of information. So it's interesting, but it's not the ideal, like I can teleport back to Louisiana to visit my family or something. So let me go into a little bit how this may revolutionize the next century. So one thing is it will allow for ultra-precise tools like measuring devices. So imagine we have, this image is a picture of LIGO, which is a gravity wave detector. And so you can imagine the gravity waves they're emitted by any object with gravity. So, but they're very small. These waves change our space and time very minutely, so hard that no instrument we have today can detect them. But using quantum measurement schemes, we are entering a regime where we will be able to detect these gravity waves predicted by Einstein's theory of relativity. So you imagine gravity waves, they kind of oscillate like this as they travel through space and time. And here, as they do that, they'll change the length of one of these arms, which you use light to interfere, and using quantum mechanics you can actually measure the gravity waves if this is sensitive enough. And that will tell us about fundamental physics, such as the Big Bang and stuff like that. Quantum computers. So, this is sort of my area of research, and quantum computers are like the holy grail of quantum mechanics right now. There's researchers, hundreds, probably thousands of researchers worldwide working on this task of building a quantum computer. And basically, they can do many things, but I'll just point out one thing, is that they will be able to simulate any element on the periodic table efficiently and how they interact with other elements, whereas our computers today, such as my laptop or even the best supercomputer in the world, can barely simulate hydrogen, which is the first element. It's the least complex. they can simulate it, but as soon as you go to helium, it blows up. It can't do it. It's too complex. But since these are atoms, hydrogen, helium, etc., they are quantum particles, so it makes sense that you would need a quantum computer to simulate quantum systems. And it turns out you can do this efficiently, so this would revolutionize any research. You don't need to do experiments, you just simulate atoms on your computer, and this would revolutionize medicine, space travel, among other things. Molecular machines. So we're entering a regime of nanotechnology where we can build little tiny machines on the scale of micro or nanometers, which is roughly the scale of atoms, and these machines may be able to manipulate individual atoms however we want. So we can start building things atom by atom, these little machines we could use to patrol our bloodstreams to get rid of cancerous material or tar. We could use them to clean the environment. We could even program them to self-replicate, send them to like the moon. They could build a base. The possibilities are endless, really. Room temperature superconductors. So, a superconductor is something that conducts electricity with absolutely zero resistance. So, what would this be useful for? Well, all the power lines we use around the world to transfer electricity, they have resistance, so they dissipate, they waste energy. So a superconductor wastes no electrical energy as you transport charge. And it's really a quantum effect to make superconductors. So that's how this plays into quantum technologies. You would, with more efficient electricity transfer and devices, you would need less power plants. Supercomputers, you could design them probably more efficiently. You can have levitating transport, so it's really the superconducting metals that allows for levitation in transport, like maglev trains, and even new improved MRI machines, which image our body. New power sources. So quantum technologies will allow for new power sources such as fusion, which is what happens in our star, in any star you see in the sky. And fusion it's the fusion of atoms, say two hydrogen atoms, and then to make a helium atom. And in this process they emit a ton of energy, which is why the sun can burn so long and so hot. If we could harness this on Earth somehow, we'd virtually have an unlimited supply of energy, because we could use ocean water to fuse, and it's predicted that we would have about 1 billion years worth of energy just from on Earth. So that's basically an infinite supply of energy. As well as solar power, so individual photons coming in, these are quantum particles